Okay, so let's talk about the rate of radioactivity, rate of radioactive decay. So what is the rate? Well, any kind of rate is how many disintegrations do we have per unit time. So the time doesn't matter. It can be per second, per minute, per day, per year, per century. So the rate is going to be proportional to the number of radioactive nuclei that we have in the sample. So here we can express it mathematically. The rate equals K times NT, where NT represents how many radioactive nuclei we have at a particular time, and K is the radioactive decay constant. All radioactive decay follows first order kinetics. We talked about kinetics in chapter 12, and so radioactive decay is first order. So all of those rate law equations apply here. So since they apply here, the half-life for first order reactions is the half-life is equal to 0.693 over K. So where K is that radioactive is the constant, and 0.693 is is the natural log of 1/2. So because it's first order. So anyway, the half-life is defined as the amount of time required for 1/2 of the nuclei in a sample to decay. So here's the relationship to K. So if you know the half-life, you can find K. If you're given K, you can find the half-life. All right, so let's just do a quick example. The decay constant for the beta decay of technetium-99 is 1 times 10 to the minus 13 decays per second. So what is the half-life in years? Well, be careful with your units. So if we find the half-life, 0.693 divided by the K value, and we get 6.9 times 10 to the 12 seconds. Well, that's a perfectly good answer unless they ask you, for example, here in years. So now we're going to have to convert seconds to years. So, okay, and so the 6.9 times 10 to the 12 seconds is a perfectly good answer, except the fact that they ask you for what it is in years. And so you have to first convert seconds to minutes, minutes to hours, hours to days, days to years. And so 2.2 times 10 to the 5 years. So that's a pretty long time. What is that? 22, 1, 2, 3, 4, 1, 2, 3, 4, 5. So what is that? 220,000 years. And that's for half of it to decay. Once you know the decay constant, we can also find the fraction of radioactive nuclei remaining after a given period of time. So remember, we can use our first order kinetics. So remember that this is first order integrated rate law. It says the natural log of the concentration at time t divided by the initial concentration, so at time 0, will equal negative KT. And again, if you know K, then you can either solve for T if you want to know how long does it take for it to decay a certain amount, or if you know the time, you can find this ratio by solving. So if you know the decay constant, let me just give you a little tip. They might give you the half-life, and then you have to find the K value, and then you can plug it into this equation. So here's an example. Gallium is used medically as a tumor-seeking agent. It has a half-life of 78.2 hours. What fraction of sample of this gallium would remain after 260 hours? Well, this might be a really important thing because if you're getting treated by this this cancer drug and it makes you more susceptible to other illnesses, you may not want to be around people until most of this is out of your system, or you don't want to be radioactive and around people until it's decayed enough. So So that's why this kind of example. So, all right, so let's see what we know. So we know the half-life, 78.2 hours. And so we can find K, 0.693 over K. Let's see if that's what comes up next. Okay, so you can, this kind of combined everything. So if you take, if you solve for K equals 0.693 divided by the half-life. So if you want to do that calculation first, so notice all they did was substitute. So let's write it up here. So if T1/2 equals 0.693 over K, then K equals 693 over T1/2. So that's what they did, is plugged this in here for K. So negative KT 0.693. You could do it individually if you wanted to. So if I took 0.693 divided by 78.2, I get 0.00886. And since the half-life is in hours, then my K is in inverse hours, because the hours is in the bottom. So I could just go ahead and figure that out first and then plug this in, or as you see, can put that in. So now, let me simplify this a little bit. So now the natural log of that ratio, which is what we're looking for, is equal to negative 0.00886 inverse hours. And what's the time we're looking for? We're looking for 260 hours. So 260 hours. So the inverse hours and the hours will cancel. So we have no units left. So 0.00886 times 260 equals, so now we have natural log of NT over NO equals negative 2.30. And then if we, let's come over here. Remember that to undo the natural log, you have to raise E. If you have E to the natural log times NT, those will cancel out. And then you have to raise this side, E to that side. So you'll have that ratio will be equal to E to the negative 2.30. Let's do 2.30. And so if you take the natural log of, or raise, you do E to the negative 2.3, and you get 0.998. Oops, 0.0998. That's the ratio, or if you want to convert it to a percent, fraction. So 0.0998 out of 1. Or rounding it, 0.0998 rounds up to 0.1. So that ratio, so here's the math done. So negative 2.304, take again, like I said, take E raised to this whole thing, E raised to raise each side, raise E to each side, the natural log cancels, and you have NT over N0, N naught. E to the negative 2.304 gives you 0.1. So I just rounded to two significant figures. So that means 1/10. The fraction is 1/10, or you could say 10%. If they asked you what fraction of sample, 1/10 of the original, what percentage, 10% of the original. Either one works. All right, what are some applications of radioactive isotopes? So You know, you hear on the one side that radiation causes cancer, but then we also know that we can use radioactive isotopes to kill cancer. So that's just one application. Let's talk about some others. First of all, it's important to remember that radioactive isotopes they're still whatever chemical you're talking about. So they're radioactive. And one important thing about being radioactive is that they're detectable. Since we know we can detect with a Geiger counter, they're detectable. But they're also now useful because whatever element they will react the same way as a non-radioactive element would act. So, you know, if it's radioactive oxygen, it reacts just like regular oxygen. But like I said, they can be detected. So that's why they're so useful, because you know where they are, you know if they're getting to where they should get to, etc. So what are some applications? You may have heard of carbon dating, which we'll talk about in a little while. That's dating rocks. How old is the Earth? That uses radioactive isotopes. So archaeological and geological dating. They can be used for scientific research. A lot of times, if you're trying to find the mechanism for a reaction, if you want to know what are the steps that happen in a reaction, you can label one of the chemicals involved with a radioactive element, and then you can follow it through the reaction, and so you know what's happening to that element throughout the whole reaction. You can use it for medical diagnosis, so you've probably heard of that, like, for example, iodine. Your thyroid uses iodine, so if you have a radioactive, if you take radioactive iodine, you can trace it in the body then, and you can see, is there a blockage somewhere, or is it being used the way it should be used? And then on the flip side, it's also, as you probably know, used as a medical therapy. And that usually is because radioactivity kills cells, and it's really good at killing cancer cells. So unfortunately, it may kill some neighboring cells, but it can kill the cancer cells. It also has some industrial uses. I think I'll talk about that in a minute. So, okay, so here's carbon dating. So let's talk about how they do that. The age of a material can be based on the rate of decay of a radioactive isotope. In the case of carbon dating, it's dating things that had one time been alive. So like trees, could be some plants, like a canoe that's made out of wood. How old is it? We can do that by using carbon-14 dating. So how does that work? Well, most of carbon is carbon-12. About 99% of all carbon is carbon-12. The other isotope of carbon, carbon-13, is the other stable isotope, and about 1% of all carbon is carbon-12. A very tiny traces of carbon-14 are also present, but they are radioactive. So you can see here about 1 in 10 to the 12th atoms. That's pretty small. 1 in 10 to the 12th atoms of carbon are in atmospheric carbon dioxide, and also in the carbon in living materials. Carbon-14 is a beta emitter, and it has a half-life of 5,730 years, so it can be monitored, and it can be detected. So if you have 1 gram of sample of carbon, and it's a living material, like a living tree, a living plant, probably not a person because they don't live that long, but a living material, it will show, you can find that it gives off about 15 disintegrations per minute. And so as long as the plant is alive, a tree or whatever, they will continue to absorb CO2, convert CO2 into the parts of the plant that it needs. And so it incorporates this carbon-14 into living tissue. As long as the plant is still alive, this process continues, and the amount of carbon-14 in that plant will will remain 15 disintegrations per minute. So the carbon-14 in the plant equals the percentage in the atmosphere, which again is about 15 disintegrations per minute. Now, what happens when the plant dies? Carbon-14 is no longer taken up from the atmosphere. So the plant has now the maximum amount of carbon-14, and it's not going to take any more in. So, but however, the carbon-14 that's in the plant starts to decays over time. So the disintegrations per minute coming from the dead tree will be less, because over the years the amount of carbon-14 present decreases and no new carbon-14 is being taken in. So the disintegrations per minute rate will decrease. So after 5,730 years, which is the half-life, the activity will then be half of the original, so 7.5 disintegrations per minute per gram of substance. So you can measure so using our first order reaction equations, we can then determine how long something has been around by measuring its activity. So we can compare it to determine how long material has been dead. Okay, so let's look at an example. A sample of cypress wood has an average activity of 7.04 disintegrations per minute per gram. That's what it is currently. Calculate the approximate age of the sample. So how long has it been, how long since it's been cut down, basically. Assume the activity of atmospheric carbon-14 currently, or at the time of that it was cut down, is 15.3 disintegrations per minute. So before I get down here, let's remember this follows first order kinetics. Oops, I got that upside down. Should be in T over in O. So we want to know what is the amount at time T divided by our initial amount. So this is going to be less than 1. And that's going to be equal to negative KT. So in the last example, we knew what T was and we found the ratio. And this time we're going to find the rate. We're going to know the ratio and find out what T is. How long has it been alive, or been dead? Sorry, how long since it's been cut down? I just wanted to point out, we said that the 15.3 is about what it is when the tree's alive, and you can see that this is a little bit more than half. 7 out of 15 is a little bit more than, well, so a little bit less than half. So it's 7.04 is less than half. So what that means is we're a little bit past the half-life. So we can kind of have an idea that it's on the order of a half-life. It's probably going to be a little bit more than 5,700 years. So that sort of helpful to keep that number in mind so we know if our answer makes sense. Anyway, so this is the equation we're going to use. What are our values? Let's get a different color. So this is our N initial. So that's initially what it is. Here's our N at this particular time since it was cut down. The time is what we're looking for. And so one other thing we need to do is find out what K is. So we know that we can take K as 0.693 divided by the half-life, in this case 5,730 years. So our K value is 1.21 times 10 to the minus 4th inverse years. So then we can plug it into we plug all those things into our equation. So there's our equation, and the natural log of 7.04 divided by 15.3, and then equals negative, don't forget the negative, 1.21 times 10 to the minus 4th inverse years times T. So that means our T is going to be in years. So first we find that ratio, which is 0.46, take the natural log of 0.46. Natural log of 0.46 is negative 0.776, And now we divide both sides by negative 1.21 times 10 to the minus 4 inverse years. Divide by that, both sides by that, and we get about 6,420 years, which makes sense. It's a little bit more than the half-life. So, your units will match. Inverse, the K is in inverse years, so our answer will be in years. So that's how we do carbon dating, similar for other kinds of dating, rocks, or as long as you know what the original count should be, which is what it is in living trees in this case. Well, rocks, we don't have living rocks, but what is it when the rock is first formed versus what is it now? Same idea. Just a note, carbon-14 dating is kind of limited to materials that are less than 50,000 years old because that's 10 half-lives, and the amount gets smaller and smaller and smaller, harder and harder to detect. So we can't really date things that were living with carbon-14 dating much before that. So other elements are used for dating things such as rocks. So one example is potassium-argon dating. Potassium-40 will undergo electron capture, and the product, the daughter, is argon-40. The half-life of potassium-40 decay is about 1.3 trillion years. And then, so if you determine the percent of argon in a potassium-containing mineral, so you're looking at the ratio of how much of it is potassium compared to argon, then we can estimate the age of that rock. Another similar way of dating rocks is uranium-lead dating. So uranium-238 will decay a number of times and it ends up with lead-206, and the half-life of that is about 4.5 trillion years. And so again, they can use that to determine the age of the rock. In this case, they can use, these numbers are a little bit, we don't know them absolutely because no one's lived for 4.5 trillion years. Anyway, is it? Yeah, trillion. So a lot of times then we can use another chemical to kind of cross-reference. And so you can use uranium-235, which is also found in the rocks, and it decays to lead-207 with a half-life of 7.7 trillion years, so not quite a trillion years. And so you can measure both of these using the same rock, and they kind of cross-check each other, and so we have an idea of what the age is. Like I said, scientific research, we can use radioactive tracers. So, for example, this University of California at Berkeley professor discovered the mechanism of photosynthesis by using radioactive chemical as a tracer. So, is able to follow the process along because it was detectable. You can read that. Another example of radioactive tracers is isotopic dilution, which is a technique to determine the quantity of a substance in a mixture. So like human blood volume was found by using isotopes and diluting it. Medical diagnoses, like I said, I already gave you an example of that. A radioactive atom will react chemically in your body the same way a non-radioactive atom will react, but now again it can be traced and monitored. So this is the example I gave you. Iodine-123 can be given to a patient to diagnose the proper uptake of iodine. So you're able to trace it, so the iodine should come through the body, and if it's used where it's supposed to be, then you can scan in the thyroid and see if it's where it should be, or if there's a blockage, or where in the body this iodine is, and to see if it's working properly. It's interesting, and we're not going to get into it, but notice that I-123 gives off gamma rays, and so remember that if it's alpha ray, you can't probably detect it outside of the body because they get they get blocked by the skin, and so the gamma rays is definitely detectable outside of the body. So like I just said, gamma radiation is preferred for diagnosis because they're easily measured outside the body. Medical therapy, on the other hand, is for the treatment of cancer, and I kind of said that earlier too. And this is just based on the fact that rapidly dividing cells are more adversely affected by radiation than slowly dividing cells. And so if you chemotherapy, well, yeah, it's using, no, chemotherapy is using drugs, but radiation therapy, you are using some kind of isotope that gives off radiation. And so if they focus it on the fast dividing cells, then those can be killed with the radiation. Sometimes some of the nearby cells might be killed as well, which is why people maybe get a burn from the treatment. It's also interesting. Oh, so here, let's talk about this. So gamma radiation from cobalt-60 has been used. It has a really long half-life, so it's been discontinued. Newer radioisotopes have been used. And in this case, alpha and beta radiation are the best because it restricts how far the radiation will escape the area of treatment. And what I was starting to say is that in regards to fast dividing cells, so cancer are fast dividing cells, and so the radiation helps on that. And just sort of as an aside, when you go to now x-rays are not exactly the same as radiation, but when you go and have an x-ray taken, they try to cover, especially they try to cover your reproductive organs, because that's the other place where fast dividing cells are. So eggs and sperm tend to be fast dividing, and so they are also a little bit more susceptible to radiation, and also because they can do damage to the DNA, which is then repeating itself. Here's just some other examples of isotopes used in medical therapies and diagnosis. So technetium-99, that M just means meta, so actually it doesn't turn into anything else, but it's excited. It's used for developing images. Thallium-201, used to locate heart disease. Iodine, like I said earlier, iodine-131 is used to measure thyroid activity and for treatment. That iodine-1, I forgot what the other one was, is also used for measurement. Phosphorus-32 is often used to locate tumors. Iron-59 is used for formation of red blood cells, measuring that. PET, if you have a PET scan, that's called positron emission tomography, which I don't know the details of it, but it's a type of radiation. Okay, so and there's some interesting industrial applications for radioisotopes. For one example, like if there's a chemical plant or some other kind of plant that has products that go through tubes or pipes or whatever, you can put a thin plug of liquid that's radioactive that separates the different products during production, and so a detector will tell you when the product is changing, so you can redirect the pipes or open a new valve or whatever. I found this really interesting. They actually use radiation to monitor how thick aluminum foil is being pressed when they roll it. So the radioactive source on one side of the strip of foil detects to a detector. It sends it from one end to a detector on the other side, and so they know how thick the foil is, and they can alter it if needed. Also, if you're a chemical plant or something like that, and you've got things running through a pipe and you're trying to find a leak in a huge maze, you can put radioactive tracers, and then you can monitor different places to see where